In this lesson right here, we're going to look at L'Hopital's rule. This is the last of the, or this is the last one of the limit rules that we're going to use for determining limits. And we can't do L'Hopital's rule until after we have done derivatives. And so since we now have derivatives, we can actually talk about L'Hopital's rule. Okay. And so here's how it goes. Now there's more to it than what I'm going to show you. There's many more different indeterminate forms. We're only going to focus on two types for A, B. If you're in BC, then you have to do the other ones. So L'Hopital's rule is a technique for determining the limit of a function when direct substitution yields an indeterminate form. Here are the two indeterminate forms we're going to be dealing with: 0 over 0 or an infinity over an infinity. These can also be negative infinities over negative infinity. Okay? So that's the indeterminate form. To do L'Hopital's rule, you must first establish that you have the indeterminate form. Then you may proceed with the rule. But you have to determine it first. Okay? Here's our L'Hopital's rule. Here's what it says. If the limit of x goes to some number of f of x divided by a g of x produces an indeterminate form, 0 over 0 or infinity, and if the limit as x approaches c of the derivative of the numerator divided by the derivative of the denominator, notice this is not the quotient rule. You take the numerator's derivative, the denominator's derivative, and that produces a limit, then that limit is actually the limit of the original one. Okay? That's what it's saying. And down here I'm just telling you that f prime and g prime must be defined on an open interval that contains the value of c. All right? So that's what we're going to be doing. Let's look at an example. I had one. We're going to look at a bunch of examples. Here we go. These are some of the ones we did earlier. And so let's take a look at this one right here. This is how simple it can become. All right? And then I'll show you my notes here that have some side pieces in here. So the first thing you have to do is you look at this saying, okay, if I try to plug in 0, I'm going to get 0 in the bottom. So that is your first clue. Now I can try and do the other techniques that we learned in chapter 2, or the limits on how to find this with trig functions and stuff like that. But I don't need to anymore. If the bottom is going to be 0, if I plug in 0 in the top, is that going to be 0? If I plug in 0 up in the top, this is the cosine of 0, which is 1, and 1 minus 1 is 0. So this is going to be the indeterminate form. You need to establish that by doing this. This is very particular here. You have to do this. What is the limit as x approaches 0 of the top, 2x? Well, that is 0. What is the limit as x approaches 0 of the bottom? That is 0. Okay? And then you write this statement. This produces the indeterminate form 0 over 0. That is what you have to do that. Okay? You do that first, then, so by L'Hopital's rule, I can do this. The limit as x approaches 0 of the original function over 5x is equal to the limit as x approaches 0 of the derivative of the bottom and the derivative of the top. That's 0. The derivative of the cosine is minus the sign, so a negative, negative, and I'm going to get the sine of 2x and then times the 2. Can I plug in 0 now? Yes, see, now I'm not going to get 0 on the bottom. So now I can plug in 0. The sine of 0 is 0, so this is going to be 0 over 5, which is 0. That is my limit, and you are done. Okay? Let's do this then right here. Find the limit of this. I look and I say, okay, if I plug in 1 in the bottom, I will get 0. If I plug in 1 in the top, I'm going to get 0. Okay? And so then I need to show that. So the limit as x approaches 1 of the numerator, that's 0. The limit as x approaches 1 of the denominator, that's 0. And this limit produces the indeterminate form 0 over 0. So by L'Hopital's rule, the limit as x approaches 1 of this function equals the limit as x approaches 1 of, now we take the derivative of the top. The derivative of the top is 1 over x, okay, u prime over u. The derivative of the bottom is 2x, okay? And we work this out. You know, you can simplify and all that kind of stuff right here. And as I plug in 1, I get 1 on top, 2 on the bottom. Right, plug in 1, that's a 1. Plug in 1 here, that's a 2. I get the answer 1/2. And there you go. So this is how you need to write this out. Okay? Every single time, don't be shy of writing it, okay? Because you need to establish that to get all the points. If you don't do all that, if you don't establish that this is an indeterminate form, they will not give you full credit. Sometimes they might not give you any credit. All right. This question also is one that they like to put in the free response area. So that's why I'm showing you how to address it. Okay. If it was in the multiple choice section, you can just you don't have to write this out because it's multiple choice. You just show that you know that this is it. You just do the L'Hopital's rule and you get an answer. All right. If I plug in 0 on the bottom, it's 0. If I plug in 0 on the top, now it has to be 0 over 0. If I plug in 0 here, I get 1. If I plug in 0 here, I get 1. If I plug in 0 here, I get 0. 1 minus 1 minus 0 is 0. So this is an indeterminate form. And so we establish it. X is going to 0. E to the x cosine of x minus 2x equals 0. The limit is x goes to 0 of the bottom. Make sure it does. Don't just say it does. Make sure it does go to 0. So this produces the indeterminate form 0 over 0. So by L'Hopital's rule, the limit as x goes to 0 of all of this equals x goes to 0, and then we take the derivative of this. This will be e to the x plus the sine of x minus 2 over 2x minus 2. Now look what happens as I plug in 0 again. I'm going to get, I'm going to plug in 0 in here, so the bottom is going to be negative 2, and the top is going to be e to the 0 is 1. The sine of 0 is 0 minus 2, and you end up getting a 1/2. Okay? Let's look at the next one. See if you can see it. Nope, I got to put it down a little bit. There we go. So let's look at this one. This is what I was thinking of. All right, so what do we have going on here? If I plug in infinity, that's infinity. If I plug in infinity, that's infinity. So what I have here is the limit as x goes to infinity of the natural log of e to the 3x plus x. This thing goes to infinity. And the limit as x goes to infinity of x goes to infinity. This is the indeterminate form my dyslexia is kicked in right here. Form infinity over infinity. Okay? So by L'Hopital's rule, the limit as x goes to infinity of this, always write the original function down, or the original problem down, equals, okay? So it's what? The limit as x goes to infinity, and the bottom is going to be a 1, but the top is going to be u prime over u. So I'm going to have a fraction up here. This is going to be on the bottom, and the derivative of that's going to be on top. So what is the derivative of all that? The derivative of all that's going to be 3e to the 3x plus 1. Okay? And so if I clean this up just a bit to see it, I haven't done anything here, I'm just rewriting it back into a fraction form, I get 3e to the 3x plus 1 over e to the 3x plus x. So that's where I'm at now. And what you notice is I still have the indeterminate form. Okay? If I do this infinity, it's still going to go to infinity over infinity. This is still the indeterminate form infinity over infinity. So what can I do? I can do it again. So now take the limit as x goes to infinity and do the same thing again. Take the derivative of the top. So this right here is now going to be 9e to the 3x over, down here is going to be 3e to the 3x plus 1. So plug in infinity again, but wait, it's still infinity over infinity. It's still this. This is still the indeterminate form. So do it again. You can keep doing this until it actually comes to a number. Take the derivative of this is going to be 27e to the 3x. Down below is going to be 9e to the 3x. And now the 3x's are going to drop out, correct? Now these are gone, and I'm left with simply 3. So that is my limit. Okay? So that's how that works. All right, so let's look at another question over here. The table gives selected values of a twice differentiable function f of x, the limit of which is equal to this, and there's my values. So what do I need to do? Okay, well, let's figure out what's going on. If I plug in 3, I'm going to get 0 in the bottom. If I plug in 3 up here, I'm going to get 6 minus 1, which is 5. F of 5 is 0. So I get the indeterminate form. The limit as x goes to 3 of the top is f of 5, which is 0. The limit as x goes to 3 of x squared minus 9 is 0. This produces the indeterminate form (0 over 0). So by L'Hopital's rule, I can take the derivative of the top and I can do the same thing for the bottom. So the limit as x goes to 3 of f of 2x minus 1 over x squared minus 9 is the same as the limit as x goes to 3 of the derivative of the top times the derivative of the inside, which is 2, over the derivative of the bottom, which is 2x. Can I plug in 3 now? Well, if I plug in 3 now, I'm going to get a 6 on the bottom. If I plug in 3 into the top, so this is going to be a 6 on the bottom, I'm going to get, again, 5. So I'm going to get f prime at 5 times 2. F prime of 5 is 7, so I'm going to get 7 times 2 divided by 6, which is 7 over 3. Okay? And so that's the answer to that one. And then our last question down here, the functions f and h are twice differentiable functions, with h of 2 being 4. The function h satisfies this equation right here when x does not equal 2. It is known that the limit of h can be evaluated using L'Hopital's rule. Use the limit as x approaches to h to find f of 2 and f prime of 2. Show your work. Okay, so I need to move that down so you can see the question. All right, so what do I know for this problem? Okay, I know a couple of things. First off, they told me that I can use L'Hopital's rule for the limit of h. There's h. So I know, okay, since I can use that the limit as x approaches 2 of the top, that's going to be equal to 0. And the limit as x approaches 2 of the bottom, which is 1 minus this quantity f of x to the third, also equals 0. Okay? So what does that tell me? Okay? So for this one, because of the functions in here, this tells me that I can plug in the 2 here and get a 0. So that means 1 minus f of 2 to the third must be equal to 0. So then solve for f of 2, and I'm going to get f of 2 to the third equals 1. So f of 2 must be equal to 1. I take the cube root of both sides, and now I have f of 2. All right? That's from that part that says that L'Hopital's rule can be used. The next one here is I told you that h is a differentiable function. Okay? So that means it is differentiable at 2. Okay? And h of 2 is 4. And not only if it's differentiable at 2, then it is also continuous at 2. Remember, differentiability implies continuity. That means the limit as x approaches 2 of h of x must equal the value of the function at 2, which is equal to 4, because it has to be continuous. So the limit as x approaches 2 of this function h is 4. So now I know that the limit as x approaches 2 of the whole thing of 1 minus this thing right here, f of x to the third, has to be equal to 4. But in the form it's in right now, it's the indeterminate form, so I can just go over here and then take the limit, because I can use L'Hopital's rule for it. As x goes to 2, this is going to be a 2x over negative 3 f of x, lower the power by 1, times the derivative of the inside, which is f prime of x. That was L'Hopital's rule. And if I can plug in 2 now, I get 4 on top, negative 3 times f of 2 squared times f prime of 2, and that has to equal to 4. Okay? We found found f of 2 to be a 1. So now I have 4 negative 3 times whatever f prime of 2 is. That's equal to 4. So I can now solve for f prime of 2 by multiplying both sides and doing all that kind of stuff and get everything cleaned up and move things around. And by doing so, I'm going to get f prime of 2 is equal to a negative 1/3. And so there you go. Using the information in a different way to solve different kinds of problems. Everything's based off of the definition of things. Everything they say in a question has meaning. So use that to help us find things. What does it mean to be differentiable? It means I can take the derivative everywhere. It means it's continuous everywhere. That's what it's meaning. Okay? What does it mean to be able to use L'Hopital's rule? That means in the original, it had to be an indeterminate form, so I can use that then to go through and figure out these numbers. So, if you have any other questions, make sure we ask them out, and we'll see this in class.